In this problem, we have a disk that is rolling without slipping, and we need to determine the linear velocity and linear acceleration of point B at this instant. So for this problem, we're going to apply the relative motion analysis again. And if we know the linear velocity and linear acceleration of point A, then we can find that those of point B, because point A and B both belong to the same rigid body. And we know their relative position. To do that, we're going to use the conclusion directly from one of my previous lecture videos, that if this disk is rolling without slipping, then its center is actually going through rectilinear motion. Its center will always be along a straight line. Therefore, its linear velocity of the center VA will simply equal to omega r, and its acceleration will only have one component. This point right here will not rotate. Therefore, there's no normal component. It will only have one linear acceleration component also pointing horizontally, and that is simply alpha r. So in this case, we can determine that if we again draw our conventional xy coordinate system, that VA as a vector will simply equal to omega times r, which is 4 times 2 along the positive x direction I, which is 8I in the unit of meter per second squared. And AA, linear acceleration of A, will simply equal to alpha times r, which is 2 times 2. Also along the same positive x direction with the I unit vector, so that is 4I in the unit of meter per second squared. So with that said, now we can try to determine the linear velocity and acceleration of point B. Because we know, or we can find out, this position vector, this is a position vector of RB relative to A. So as you can tell, RB relative to A equals to, we will have negative x component, so negative 2 times cosine 45 degree I, and then a positive y component, 2 times sine 45 degree J. Therefore, this right here simply equals to negative square root of 2I plus positive square root of 2j. And I'm going to evaluate that later. Therefore, we're going to write the relative velocity equation, that VB equals to VA plus omega AB vector cross RB with respect to A. VB is what we're trying to find out. VA is known, 8I from this step. Omega AB, omega is 4, but because it is rotating clockwise, so that is actually a negative 4K cross negative square root of 2I plus square root of 2J. So that equals to 8I. And then K cross I equals to positive J. 2 negative signs cancel each other out. So this equals to 4 square root of 2J, which is 5.66J. And then K cross J equals to negative I. So we have another negative sign here, cancel each other out. So this equals to plus 5.66I. So after we evaluate that, that equals to 13.66I plus 5.66J in the unit of meter per second. So that's VB as a vector. So if you are curious, what is that direction? Well, the direction is actually, if you recognize that this point right here is also IC, instantaneous center of zero velocity, and this right here is going to be your RB with respect to IC. Let me just use a vector right here. then VC is going to be perpendicular to RC. So this will be the direction of VC. And that's what this vector is about. So that's the first part of this problem. And then we move on to write the equation for AB, which equals to AA plus alpha AB cross RB with respect to A minus omega AB squared RB relative to A vector. So AB is what we need to find out. AA is known from here. So 4i. And then alpha is also negative 2k, because again it's clockwise. And then cross negative square root of 2i plus square root of 2j. And then minus omega AB is negative 4 squared, and then negative square root of 2i plus square root of 2j. So we do the evaluation, and this eventually equals to 29.5 I minus 19.8 J in the unit of meter per second squared.